Continuing on a similar topic, Thomas Rizzo will talk about collider tests of quantum gravity.
Oh, okay. So I want to thank the organizers too for invitation to talk. So I want to thank the previous speaker for introducing some ideas that you're going to hear more about in here. So we don't know what the theory of quantum gravity is, and so but we want to try to ask the question: is it possible to try to test this theory, whatever it is, at something like the LHC? And as you've heard, this may be possible. It's possible if there's some way that the Planck scale could be at the TeV level, then perhaps there would be some effect to be seen. Obviously, if this is not true, this is a hypothesis, and this is something we'll find out whether it's true or not. If the Planck scale is not at the TeV scale, then I don't think the LHC is going to have very much to say. But from now on, we're going to entertain this possibility, as you already did for the last 45 minutes. And you could ask, how is it possible to get TeV type implant? Well, we heard a nice talk on Monday that it's possible even in 4D if there's lots of extra states that cause the RGE for the effective gravitational coupling to run rapidly. But more frequently in the literature, you hear this being discussed under the subject of TeV scale extra dimensions. Now, maybe there's some other way of doing this that we don't know about, so I can't talk about that. So I will talk about these things within the TeV extra dimension scenario. Okay, so ordinary TeV scale extra dimensions are based on general relativity and the Einstein-Hilbert action. Even in d dimensions, this is, of course, just some effective theory because once you get to, for example, collision energies of order of the Planck scale, you get the strong coupling, and the theory, unlike the standard model, is not perturbatively renormalizable and associated with this bad UV behavior. Now, a particle physicist doesn't like this, and so we ask the question, how do we deal with this problem? How can we restore a good UV behavior? So long ago, Weinberg tried to address this issue, and he said there were maybe only a few possibilities. The most obvious thing to imagine is a subject we've been talking about here a lot. Einstein-Hilbert is incomplete. There's new physics, there's strings, there's loop quantum gravity, there's whatever. And that all comes in and it saves you, and everything is nice. Another possibility is the gravitons themselves are not fundamental objects, that they're composite or something like that. Another possibility is maybe when people are trying to do perturbation theory, if they reorder the terms in the right way, whatever the right way is that hasn't been discovered, suddenly the theory would make some sense. And the last possibility is perhaps the lack of perturbative normalizability is just an artifact, and really what you should do is think about the theory non-perturbatively, and perhaps due to asymptotic safety, you have non-perturbatively renormalizable interactions. This is possible. You have some experts here in the audience, so when I get to talk about this later, if you have questions, you can ask them about it. These possible ideas that are listed above here, we want to find out that if any of these things are true, how do we test it at the LHC? So obviously, the first thing you have to do is you have to find TeV scale extra dimensions based on the classical GR, and then look for modifications to them, okay? Because it's the modifications which are the quantum stuff, which you guys are interested in. So, two steps. One, find TeV scale extra dimensions, and then look for non-GR type physics, whatever that means, associated with it. So there's a whole lot of stuff. We just heard some nice talk about black holes. We also heard mentioned string excitations, which I'll talk a little bit about. The possibility that in an interaction, gravity becomes weaker at the higher energies because of this fixed point. People have argued that maybe you can see some effect of higher curvature terms, space-time non-commutivity, Lorentz violation in extra dimensions. I haven't heard that in here. And people have actually talked about causality violation, something that in principle you could also measure at the LHC. Now, I'm not going to have time to talk about all of these things, and when it comes to any of them, I'm completely agnostic. And I won't advocate anything here, but I'll just take maybe 3 of these guys and talk about how you may or may not be able to see singles of them. Okay, so let me just quickly remind you about TeV scale extra dimensions as far as we're concerned. These theories are now about a dozen years old. There are only 2 toy models out there that involve gravity. One is the ADD model by these gentlemen, and the other one is the Reynolds-Sundrum model by these two. Okay? These two models have very distinctive signatures, and they were not motivated to deal with general relativity at all, but to solve the gauge hierarchy problem. That is, why is the Planck scale so much larger than the Weak scale? And as you heard, what they want to do is they want to bring the Planck scale down to the TeV scale. That's the goal of these theories. Okay, so very quickly, in the ADD model, the idea here is that you have n extra dimensions. The standard model lives on a 4D hypersurface in this 4 plus n dimensional space. Gravity is everywhere. These extra dimensions are compactified. In the simplest picture, they're compactified on a torus of equal radii. So the volume of the extra dimensions is 2 pi r to the n. And then if you write down the action, which is just n-dimensional general relativity, n star is the true fundamental scale, which is supposedly a few TeV, and you go through the calculation, you see that there's a relationship between the 4D Planck scale and the fundamental scale. So if you want this number to be of order TeV, and this number you know, then this tells you the volume, and hence that tells you what the size of the radii are, and that also then tells you the masses of the Kaluza-Klein excitations. So what you do in these models is that you make an expansion, you make a linear expansion of the graviton field around the flat background in the usual way. Then you couple it to matter, which is localized. You do all the usual things that you have to do in a KK model. You do a KK reduction, you expand the tower, you put the standard model on the 3 surface, pick an appropriate gauge, and integrate over the extra dimensions. And then you write down the Feynman rules. So the radii that you get out for these extra dimensions depend on the number of extra dimensions you have. If you assume there's only one extra dimension in this model, you're in trouble, because it means the size of this dimension is solar system size. Clearly not the case. When you have 2 extra dimensions, they're of order 100 microns or less, and this is being probed by tabletop experiments. When the number of extra dimensions is bigger than that, there's no direct bound from tabletop or astrophysical experiments, really. No direct bound. The lightest KK masses increase as 1 over r. Okay, so people have spent a lot of time and they've written down all the Feynman rules. I'm not going to bother you with that. Okay, so how do you test these things? Once you have the Feynman rules, you can go ahead and calculate. So these graviton KK states can be emitted in the collision of 2 standard model particles. So, for example, at the LHC, I can take a quark from one guy and an anti-quark from the other one. I can scatter them, and in the scattering process, I can make a gluon and a KK tower of gravitons. These KK tower of gravitons, every one of these guys in the tower is very weakly interacting. And so when it's produced in the detector, it just streams right through as missing energy. So what's seen is these, in this case, this gluon, which turns into a jet. So what you see in the final state is a jet with nothing balancing on the other side. This is called a monojet. And this is the process which has, at least for graviton emission, this is the process that has the largest cross-section and hence the largest reach at the LHC. A second thing you can do is you can exchange gravitons between pairs of standard model particles. Okay? So for example, I can take, again, a quark and an anti-quark. I can make gravitons, and then these gravitons can go back into, say, E plus E minus. But the standard model also does that. I can do that with a photon or a Z boson. So what happens now is that the exchange of gravitons, the amplitude for that, interferes with standard model exchanges, and one could look for deviations from the standard model. Okay, so that's ADD in one slide. Now, Reynolds-Sundrum model is somewhat different. There's only one extra dimension in the Reynolds-Sundrum model, and I'm only going to talk about the original one here, because otherwise, if I put standard model fields into both, things get complicated. Again, here, all the standard model fields are localized to what's called the TeV brane. This bulk, this extra dimension is not flat. It's warped. It's conformally. Okay, it's warped. This is the metric for that, and this is ADS5. This model, the predictions are different. The KK gravitons now have discrete masses, which are separated from each other by numbers of order a few hundred GeV to a TeV. The masses are set by the roots of the Bessel function. The couplings of all these KK gravitons have an inverse strength of order TeV. And so what the signal is here is that anytime you have a 2-to-2 standard model process where I take two standard model particles, I annihilate into one of these KK states, and back into standard model particles, I produce a resonance. Yes?
What happens if you consider the alternative model where the other brane is at infinity? Okay, you don't solve the hierarchy, but...
No, you can do that, but then the physics is closer to ADD.
Okay. Is it exactly ADD? That's my question. Or
Exactly no.
Exactly no.
Okay. So, So this is the basics of RS. Now, okay, for us, what we want to do is not look for the predictions of RS and ADD. We want to see how they change when one of these quantum gravity scenarios are added to these two models. So, for example, if you try to take asymptotically safe extra dimensions and look at the signals for what these may be at colliders, again, we have some experts here. The idea here, there should have been a talk about this, because I think this is really interesting stuff. Okay. So the idea here is that there's we're using the Wilson picture, there's an RGE analysis of a truncated version of the gravity action. One looks at how the coupling of the form dimensionless coupling of this theory runs with scale, and one finds that in fact not only is there the usual infrared Gaussian fixed point, but there's another fixed point which is non-Gaussian, and this is supported in fact at some level by some lattice calculations, so this is perhaps even true. I won't go through the technical details at all here, but at least in some approximation you can get an analytical result for this, which tells you how the gravitational coupling runs with scale. If you start at some scale mu0 and ask what the scale is at another mu, this tells you how to relate those two. You can write this back in terms of what I like to write as the effective Planck mass, if you like, which will appear in couplings. So the M here is what goes into the action, and this is how it evolves with scale mu. So if you look at the interaction of matter with the gravitational field, you know it goes like 1 over m effective to some power, in this case d minus 2. And the way one could describe it, this is not a unique way of describing it, is thinking of just taking the usual coupling that you have and scaling it by a factor, which particle physicists like to call a form factor, which looks like this. So here's that scale that you're trying to evaluate the gravitational interaction at. Here's the fundamental scale, and here's some model-dependent parameter, which comes from the slop on the previous slide, which I didn't go into, which is some number of order 1. And delta is the number of extra dimensions. So for the moment, we're going to treat delta t as some order 1 free parameter that depends on the details of the model that I don't really know too much about. So if you look at this form factor, you see that as the scale mu gets larger and larger, f cuts off the interaction. F gets smaller and smaller, and so this thing, instead of growing, it'll grow initially with, say, center of mass energy, but at some point this form factor takes over, and then the interaction gets weaker again. So, for example, if you have an S-channel process, where, for example, you're exchanging gravitons, and you do, for example, QQ bar through a graviton into E plus E minus, the scale for that process, it's natural to take the center of mass energy. Now, maybe that's not exactly the scale that you should take, but this is not a next to leading order QCD calculation. This is a gravity model, so there's some problems. Okay, so what you're going to see now is that putting this factor f into the predictions of both ADD and RS change their predictions. Okay. This parameter t, which I said is an order 1, you can get some constraints on it if you sort of want to make some nice requirements on the theory. If you want the large S behavior of the theory to satisfy unitarity, that means twice the real part of the scattering amplitude be less than 1, then you can get a bound on t. So for example, here's the scattering of, thinking about a thought experiment. This is a thought experiment. I'm scattering 2 Higgs bosons elastically through graviton exchange. That's a thought experiment. Okay? So here it is, but you can calculate it because it's there. Okay? And this is what the maximum value of the cross-section, or the maximum value of the amplitude is as a function of t. And we don't want this to be less than, greater than 1, so as long as t is, order is 1, less than 2, let's say, then I'm completely fine. If you do this in the Reynolds-Sundrum model, you get the same bounds. Okay, so what is this? So now I'm at the LHC. This is the 14 TeV LHC, because that's what I made plots for. And I'm doing exactly the experiment that I told you about. I take 2 protons, I annihilate them, and I make a pair of leptons and any other thing else I want. And this is a plot of what the invariant mass distribution of these 2 leptons looks like. This is the standard model prediction, assuming there's no new physics whatsoever. Okay? If I just had ADD and nothing else, if the fundamental scale were 2.5 TeV, just to draw a plot, at some point I would, the number of events would diverge from the standard model, and I would get this line here. Hard to miss. Now, if instead I had this form factor, and I assume t equals 1 just for demonstration, and the number of extra dimensions was 2, 3, 4, 5, 6, 7, then instead of this guy, I would get one of these guys. So it lies sort of in between the standard model and the trivial ADD calculation. So I can make all sorts of different plots. I can fix a number of extra dimensions and then show you how it depends on t. You see it's fairly sensitive to t. If t is very large, you don't get much of a form factor effect, and so you're pretty close to ADD. If t is small, the form factor is very effective, and the cross-section gets suppressed down to the standard model. In fact, it may be so close to the standard model that it may be difficult to even tell that you have anything new. So that's important to remember. Different energies. Instead of exchanging gravitons, I can emit gravitons. And so what's observable here is jet plus missing. So what you do is you measure the spectrum of the jet that comes out. Now here, I have to put in something for mu, but it's not the center of mass energy in the collision. It's some other thing associated with the energy of the jet. Well, is it the transverse momentum of the jet? Is it the jet energy? I don't know. But the results depend on which one I choose for the scale mu. So this is what happens if the scale is the PT of the jet. Okay? So the histogram is the standard ADD prediction, and these data points correspond to what would happen if you put in this form factor. Now you see here, the PT of the jet is, unfortunately, sufficiently, the PT of the jet is, believe it or not that big. And because of that, you don't see very large deviations from the ADD case. However, if it's the total jet energy, which is bigger than just its transverse energy, okay, then you see a somewhat larger deviation, and you see a suppression of the number of jets compared to ADD. And this is what you would get in other cases. So what happens here, the monojet rate and the shape of the jet energy distribution is changed when you include these form factor effects. In the Reynolds-Sundrum model, something else happens. In the normal Reynolds-Sundrum model, you get this set of Kaluza-Klein resonances. Actually, you get this red line here. The first resonance is nice and narrow, and the next one is not so bad. The third one starts to get wide, and when you get up to the fourth, fifth, etc. KK resonance, these things get very wide, and they get washed out, and you don't see them. The reason is because the width compared to the mass is getting large. It's a strong coupling situation. That's GR, okay? When I turn on these form factors, the form factors start pushing back on you, not letting the coupling get very big. And so the resonances stay narrow now. So, for example, you get these nice sharp guys instead of some smeared out thing.
So what is mu in this case?
Mu in this case is root S. Okay, something completely different. So, we heard already some comments about string excitations. So you know what they are. These are Ricci excitations of standard model particles. Yes?
Sorry, maybe before I proceed, a very naive question about asymptotic certainty. Is it clear that those theories are ghost-free? Because look, gravity is a purely attractive force, right? So if it becomes
let's ask an expert.
No.
Are you the expert? Are you the expert? I don't know if you're the expert.
I actually wrote the second paper in the subject.
Okay.
And then I left it because there were both.
Okay.
But I think it is.
So they are both. That's the
But
answer.
I had a different issue about unitarity. Because you inserted this whole phrase about destroying unitarity. Does that mean the standard calculations With Randallson could violate unitarity at the tree level?
Oh, absolutely.
Isn't that an issue?
It's the same issue that you have in GR. GR violates unitarity too.
Well, we don't take GR seriously in this regime
Well,
for that reason.
but this is why you want to put in a quantum theory, so this doesn't happen.
Good.
Yeah. I mean, if you just naively extend it, you get this thing which you don't want. Okay. And what asymptotic safety is doing for you here, one of the things, is stopping that bad thing from happening. Okay, and restoring unitarity, which is something you might want in a quantum theory of gravity. For sure.
So if you are saying this form factor cannot arise within a unitary theory, then it's not a pure. Right?
If it can't arise within
Yeah, if the theory that gives you this form factor has a ghost.
Well, I don't know if it has ghost. Where is... Yeah, he's the expert.
The unitarity is a dynamic question, which also depends then on the running of the couplings, and there are certain there are proposals how what negative mass states which arise, for example, in the R-squared theory, like studied in the 70s, like that this can be cured by running off the couplings, because you might have a coupling with another sign at the fixed point.
But that's very difficult to understand. By the moment you tell me that a theory that is purely attractive becomes weaker at shorter and shorter distances, I think that's very indicative that a ghost must be in a theory.
No, for sure. And
Does this happen in the 4D theory?
In 4 dimensions, there is an asymptotically safe theory, and it has ghosts and problems with causality.
Okay.
It's the theory in which you add all the dimensions for terms, the vowel square plus the R square plus the R plus the lambda.
Oh, because they don't combine two Gauss-Bonnet terms, say.
Right. It has a non-trivial fixed point. It's a beautiful theory, but it's just unstable and not unitary.
Okay. Thanks.
Okay. So I was going to tell you about looking for Ricci excitations of standard model particles, something that, again, we heard a little bit about in the last presentation. You want to see, this is probably a rather unique signature, because seeing excitations with a common mass for all of the different particles in the standard model, something fairly unusual. One of the problems here is making, even from a phenomenological point of view, making a reliable theoretical calculation for relevant processes. And there's only, I think, as far as I understand, there's only been done for a few. The channels which are perhaps the most interesting and which provide the greatest reach at the LHC are ones that are either QCD induced, such that you're building on top of strong interaction, or ones which are very clean, which involve, for example, lepton pair production, like we saw in the previous presentation, Trillian. So you all know this better than I do. The way these Ricci recurrences come in is that it's basically the standard model amplitudes in various channels get rescaled. And then when you expand this beta function, you see that there are poles of order the square root of n times the string scale, which, again, we're thinking of as the TeV scale. You have to incorporate make some minor changes here and incorporate finite widths for these resonances. But at least from a phenomenological point of view, as far as I can see, this has been done successfully in the literature by an army of people. And these resonances look something like this. For example, here's a dijet resonance. So, for example, in glue-glue to glue-glue, you can make a resonance like this. Okay? And because the width-to-mass ratio is reasonably small, of order 10%, this thing isn't very wide, and it's consistent with the mass resolution of the machine, and so you're able to actually see this. And apparently, my understanding is that this is all reliably calculable and well understood. So, you would not only want to see this in one channel, you would want to see it in lots of channels, so you convince yourself you're not just seeing some Z prime or something like that. So you see it in a dijet channel, you see it in, say, a dilepton channel, and you'll see in the slide or two, you'll see it in the top quark pair channel. So just observing one resonance is not enough because lots of new physics predicts resonances. And then when you see these resonances in various channels, the next thing you want to do is convince yourself that you're really producing multiple resonances which are sitting on top of each other which have different spins. This is also very different from anything else that occurs in extended models of other kinds. This is not going to be all that easy to do because if somebody gives you an actual angular distribution, one has to deconvolute various different parts of it. There are detector acceptance cuts that one has to deal with. And if the string scale is sufficiently high, this is going to be very difficult just because of low statistics, and you're going to need very high luminosity to do this. You'll only be possibly even remotely convinced that this is true unless you see this in lots of different channels. And for example, tops. Okay, the last thing, you might imagine that when you're starting to get to towards the Planck scale, that there's extra terms coming into the action now. And maybe you can parameterize the leading effect of these things as some higher curvature terms. And people have studied these things in the literature. Most of this has gone into black hole physics, but it's possible that you can just look at ADD and RS with higher curvature terms included. And this type of work's also been done. So, again, you're more of an expert on this than I am. In perturbation theory, when you add higher curvature terms to the d-dimensional action, you end up getting non-graviton degrees of freedom, which are either spin 0 or spin 2. If you don't do anything special, these spin 2 guys are dangerous. They're ghosts. Okay? And you have to get rid of them. At least particle physicists said you have to get rid of them. And you can ask, if you have these type of things, how do ADD and RS predictions get changed? So you can write down, there's many, many models of these type of things. You can write down some action, which is some general function of R, and say the two quadratic invariants that you could write down. And then what you want to do is to get interactions and propagators and such. You need to expand this thing in second order in the background metric. And this is relatively easy to do with ADD and RS. ADD is trivial because it's Minkowski space. RS is relatively easy to do because it's just anti-de Sitter space. So you can do this. Okay. So for example, in ADD, when you look at the interaction now between localized standard model sources on this brain, there are now various contributions to the scattering amplitude. This is the ADD contribution. So this is the usual piece that you get in ADD. These are the KK masses that you have to sum. And then you get an extra piece, which is spin 2, with a minus sign, which is a ghost. Okay. However, it has a non-zero bulk mass, which is M2, which we'll come back to in a minute. And then there's, in principle, a scalar piece, which is just the trace, the product of the traces of the two stress energy tensions for the two scalar model fields that are localized in the brain. Now, if you want to get rid of this guy, a fast and dirty way of getting rid of this guy, since you have these various dependencies on, F has these various dependencies on R, P, and Q, one could choose a function in such a way that the value of M2 is actually infinity, such that this thing has been removed. And so you can do that. And one way you can do that is by choosing a combination of the dependencies of P and Q in F in such a way that, just algebraically, this becomes infinity, and that removes the ghost issue. You also have to be careful that you don't end up producing any tachyonic fields in the scalar sector, and that puts a constraint on the second derivative of F with respect to R. But other than that, you can go ahead and calculate with this. And of course, you have new Kaluza-Klein excitations associated with the towers here. Okay? They're different from the graviton KK excitations in two ways. One, their coupling strengths are much smaller than the KK gravitons are. The reason for that is because they couple to T squared and not T mu squared. So T is proportional to the, if you like, the mass of the standard model particles that are on the outside lines. So for example, imagine WW to WW. W is relatively heavy. This cross-section, this amplitude, the cross-section, would be smaller by a factor of NW squared over the center of mass energy squared. And then there's a numerical factor out in front because of these guys, which is of order of 100. So this thing produces an effect which is extremely small and basically impossible to see in ADD. The situation in RS is a little bit different. You can do exactly what I just did before for the Randall-Sundrum model, and you can again make this expansion. G is Gauss-Bonnet in 5B. And this is the trunk, it gets truncated here. And you find that the physics in RS changes a bit more than what happens in ADD. There are certain relationships between the parameters in RS, they get modified. There's a relationship between the bulk cosmological constant, the curvature, and the fundamental scale, which now picks up extra terms from these extra terms of the action. The relationship between the Planck scale and the fundamental scale gets changed by, again, some function. The masses, the bulk mass of the extra scalars that are in that are now in the RS model are determined by this extra parameter beta and the fundamental scale. And when you go back and calculate their equation of motion, the masses and couplings of these extra scalars are now dependent on Bessel functions, something that always happens in Randall-Sundrum model. And the mass of the lightest extra scalar field in this model then depends on the value of this m sub s that you have to calculate. And as m sub s over k, which is the curvature parameter of the model, increases, the mass of the lightest scalar kk increases. When this value is equal to 0, then the scalar and the graviton mass are the same. But there's no reason for this to be 0. This is principal some number of order 1. So you imagine some order 1 change in the mass of the scalars compared to the graviton kk towers. The relative coupling strength, apart from the fact that this guy goes as t squared and not t mu nu squared, there's again some overall numerical factor which suppresses the coupling of the scalar kk's compared to tensors. Now, even though you're producing extra scalar resonances here, they're still hard to see because they're very narrow. Because the coupling compared to the Randall-Sundrum resonances are again down by mass of the standard model particles squared over s, or in this case, the mass of the kk squared. So this is a big suppression factor, but nobody's done this study to find out whether these things can be seen or not. My bet is probably not, but nobody's done the study. Okay. So I looked at 3 different possible extensions of RS and ADD. This is perfect. If the scale of quantum gravity, or whatever the theory is that replaces Einstein gravity, if the scale is, the Planck scale is order of UTeV, then it may be possible, at least in some cases, to see some unusual direct effects at the LHC and linear collider as well, but I didn't talk about that. Unfortunately, we have no real idea about what this theory is. We can only speculate then on what possible signals there may be. So, well, there you are. Here's our friend. Okay. So there are very many models with a wide variety of predictions. Okay. Many of the current scenarios can be tested at some level, but you see that it depended on constructing modifications to toy models, ADD and RS. These things could be completely crap, in which case, I don't know how we're making, what kind of predictions we can really make. And then you have to hope, or gamble, or ask this guy, and hope that the LHC's capabilities to see phenomena over a wide range of possibilities is good enough that whatever the TeV quantum gravity theory is, you'll still catch it, whatever it is, even if it's not one of these theories that I told you about before. Now, a real hope and dream, which would be wonderful, is that if it is something that's nearby, maybe the LHC can provide enough experimental data that you can reconstruct the theory from the data. Okay? In other words, have the data tell you what the fundamental theory of gravity is. Well, it probably can't do that. It'll certainly narrow down among maybe an infinite set of possibilities. It certainly could narrow things down a lot. This would be possibly the best possible outcome, because if you really want to build a new theory, what you really need is a lot of data, and not things that are indirect. You want to have direct measurements, and this may provide that way to do that. So anyway, we're looking forward to some kind of discoveries in the LHC. Nobody knows what it's going to find, but maybe this is what's going to find. but maybe this guy. So. Yeah.
Yeah, so when you're, it was very interesting to see what you said about adding higher dimension terms, higher curvature terms. But in the case of Randall-Sundrum, I mean, there's a natural five-dimensional term which should be there, which is the five-dimensional Chern-Simon action of the gravitational connection. Has anybody considered the effect of that?
I have not seen that done, but that doesn't mean I've never seen it. But somebody could have done it, but I have not seen it.
Yeah, I mean, I would think it would be there. And since it's dimension 5 in 5 dimensions, it's the only dimension 5 gravitational term in 5 dimensions, it would be important. And it breaks parity so that its phenomenology.
I'm sure the physics would be very interesting. Maybe somebody has looked at it and I just don't recall.
I have a question that I asked in a few occasions. I have never understood the answer from this D-brain worldview. These particles that are confined to the brain is supposed to have a width or be infinitesimally thin.
In these idealized cases, they're zero thickness. Of course, you can make a model where they're finite, where they have a finite thickness.
But then I have energy contribution from the momentum uncertainty that has to be associated with the high localization in this direction.
Well, okay. Now, we don't know what the localization physics is, but you really have to ask the question, that's only true if these particles know there's a fifth dimension. If they don't know, if they're truly 4D fields, they don't probe the extra dimensions at all. So then they would have no uncertainty, there's no momentum, there's nothing. They don't know there's a fifth dimension. They can't have an uncertainty principle associated with the fifth dimension.
But they are described by a wave. They are described by a wave function that has to be localized there.
The wave function is a pure 4D wave function. They don't know. They don't have a 5D component in their wave function at all. Because that's the way these models are constructed. So the claim is that these particles don't even know that they're extra dimensions. So they don't have any uncertainties associated with things they don't even know. You have to know about the extra dimension to have an uncertainty associated with it. I think there probably is some solid state analog.
Well, one way to view that would be that whatever localizes those fields on the brain, or whatever you want to call that, here it's actually more surface, not a brain, right? Comes perhaps with a different energy scale. Hopefully a larger energy scale than the effects you want to study on the brain.
Yeah, that would tell you what the size is, but it wouldn't help you with the uncertainty question.
That's true, yeah. Yeah, that's true.
I think the only out from the uncertainty thing is to say, by whatever, that these fields are truly 4D, and they don't know anything about the extra dimensions.
Well, we know it's over-idealized.
Yeah, and of course it's an idealized,
because the
extremely
brain
idealized.
also will have transverse momentum.
However,
Quantum
if
mechanics.
the brain, it depends what he means by uncertainty, Daniel. And I think if the brain fluctuates itself, that's what most likely.
Sure.
Then the gravitons would know, because the gravitons propagate.
And there's extra fields then associated with the brain, the brainons associated with the brain.
And there is where the formation, when you hit two particles, these fluctuations of the brain would affect the formation of the black hole itself.
Exactly.
So if we are, then it goes back to what Daniel asked originally. If we are in a foam situation where the foam is TeV scale, it may be drastically changed properties of the foam black holes because of these fluctuations. So, but that is, you cannot calculate because unfortunately this is not derivative.
You see that the beauty of the construction of early beginnings is that you do the calculation in a regime where gravity is still weak, so you don't care about those details. You prove there's a closed trap surface before you have strong gravitational fields.
It's a classical calculation.
Exactly.
That's the point, right? It's not you don't have an S matrix involving a real black hole.
Yes, not possible.
No, but the question is different than this. What I'm saying that when you have a brain fluctuating, it's a different thing than what Giddings did. That's what Daniel did. What's happening when you have uncertainty in the position of the brain.
It's a question both to you and perhaps the previous talk. I mean, all this rich phenomenology, to your assessment, the implications for cosmic rays, for the highest energy cosmic rays, where we have studied center of mass processes which are very significant. Of course, we don't have detectors around them, but the periodic observatories.
There are bounds on, as you know, black hole production in the atmosphere from cosmic rays. And this does put a constraint on, for example, the fundamental scale.
Yeah, this is the
But
theory.
would you say it has been fully exploited through that? I mean, isn't there?
Exploited.
I mean,
What does truly exploited mean?
I mean, everything works as expected for, say, the spectrum of cosmic rays over a broad band, which corresponds to center of mass energies, say, for the collisions, potential collision with CMBR photons, which are center of mass energies even well above the LHC. So I'm very surprised that there is so little to be gained.
Well, that's why we know from the atmosphere. I mean, we know the constraints from the cross sections of production in the atmosphere. I mean, that's why we know the LHC isn't going to kill us. I mean, if there were black holes being produced in the atmosphere and they were dangerous black holes, there wouldn't be an Earth a long time ago. You know.
The problem with cosmic rays is that when you have proton-proton interactions of those energies, the cross-section is subatomic compared to the cross-section. So when you have proton air showers who are there may be black hole layers, but the branching ratio is 1 per million. So you have to look at the neutrino induced showers. And those are horizontal showers. And my understanding is that the RNA is looking at horizontal showers. So one has to estimate these are very high energy horizontal showers, so 10 to the minus GeV. And I'm not sure if the array you have any detection or you are even looking at
How about photopion production? So I have a proton hits a photon, okay, in such a field. And you have some scenarios where you could have gravitons escaping into extra dimensions.
Sure.
So I mean,
There are some constraints.
the whole energy balance of the cosmic ray spectrum works well, and we are
People have looked at this, and there are constraints. I mean, there are constraints.
But the problem is you don't know what's coming in. You don't know the original energy. You don't even know whether it's a proton or heavy ion. So this is limiting you very
You
much.
have to reconstruct.
So one more question, or everybody?
Everybody wants coffee.
Everybody wants coffee. Okay. Thanks.